Okay, thank you very much for the chairman's introduction. I just brief to show my titles. And today's talk is we talk about challenges of traditional manufacturing technologies, because I mainly work on metal forming as the chairman, Professor Fu mentioned, and I concentrate on metal forming. But most of people here and at many universities work on very advanced manufacturing technologies, like nanotechnology, whatever, and I work on very traditional manufacturing technology. As mentioned, I come from Imperial College, UK, and we established two companies. I'm founding director of the two companies, actually three companies, spin-off companies to commercialize our technologies developed over the years. And many people I know here and has been yes, many people here has like Professor May and Professor Fu been in Imperial College, and I walked around the campus. I found this campus is much bigger compared to Imperial College London, and we are just around here. These some buildings, but we have got a couple more buildings here, and that belong to Imperial College. It's very small, comparably, but one of the department is important. That's the mechanical engineering department. That's I allocated here. And if you can find Hyde Park in London, you can find Imperial College very easily. You're welcome to visit us if you haven't been there. Not very sure oh, okay. And just give you a brief introductions about Imperial College if you haven't been there. And in the probably people know these World University rankings. We call the QS ranking. And in the last session, we are number 6 in the world ranked, and it's fairly okay. But we are most interested in is REF, and previously called RIAM, started in 1986. Every 5 years, we do ranking at universities. And REF represent Research Excellence Framework. And 2021, that's last results received. We are number 1 in the UK universities. So this is what we're proud of. And our group, Metal Forming and Materials Modeling Group, and I'll give you brief introductions here. And it's established in 2008 and is fairly new. And at that time, I moved to Birmingham, to Imperial College from Birmingham University in the UK. And I bring all the people there and establish a group at Imperial College. And currently is the largest research group at UK universities in metal forming. We have 5 academic staff and about 50 researchers. And we work on a wide range of research areas nowadays. In last 5 years, we published about over 200 papers. We attracted over 10,000 citations on these. In the meantime, we received a lot of funding from government, industries, etc. Over 130 million pounds being received over the last few years. And also in the group, we established 4 research centers and 2 laboratories, joined the research labs. And we have, as I mentioned, we have 3 spin-off companies to commercialize our research results at from Imperial College. In 2022, we received the President Medal. That's in Imperial College. We have got around 500 research groups, but we've been recognized that's the best research group within Imperial College. That's the probably most prestigious award at Imperial. And back to our topic today. And I highlighted these traditional manufacturing technologies. And I mainly concentrate on this and give you introduction and mention about metal forming technologies and applications and the global requirements, new global requirements, then innovations on the traditional manufacturing processes at end. I give you conclusions. Probably most of people here, I believe, work on engineering. You may know from your undergraduate studies, you may know the main manufacturing technologies, or we say traditional manufacturing processes. One of them is machining, that's cutting. And we can recognize this as remove materials. You cut the materials away to get high accuracy and so on. And this includes milling, drilling, drill a hole, water jet cutting, laser cutting, EDMs, and I just talked to a student work on machining. And this is very popularly used nowadays in industry and been developed, we say, used for a few hundred years. And another process is casting. And the main is considered from the liquid to solid. We probably people know this sand casting, die casting, gig casting now becomes popular. And 3D printing, probably additive manufacturing is kind of casting process from liquid to solid as well. In this process, we consider this is add materials. You put material, add materials from the liquid to solid. Then you can manufacture the components with a complex, very complex shaped components. And it's such like this, and being well known and being used in industry for many, many years nowadays. And the third technology most commonly used is the metal forming. It's a forming process. And compared to machining, casting, and forming, those three, we say the most commonly used. But forming, some people call it forging, or in English, we call it metal bashing. And you can see a lot of traditional workshops and can see these kind of technologies. Nowadays, you still be able to see in some of the market, like you make jewelries, you still use handmade. This kind of jewelries is kind of forming process because gold is easier to deform into the shape. And let's see if it works. Oh. Sorry. Yeah, okay. Yes, and this is a BBC program that introduced the manufacturing processes. I like the word. And in forming, that's compressive forming, that the metal becomes stronger and tougher. That's the important words I picked up, because this is better than any other technologies. I mentioned another two, because the material becomes stronger and tougher. Metal forming, there are many processes like rolling, stretch forming, stamping, seal plastic forming, manufacturing various kind of parts. When you manufacture components, but normally you try to think whether it can be formed or not, because for metal forming, you do not remove the material. You do not, not like cutting, remove the material, not like 3D printing. You add a material. This is just shape changes. We say the volume keeps constant. Do not change the materials, just change the shape of the materials. That's the, we say, plastic deformation of materials. That's the metal forming process. And most importantly, the material becomes stronger and tougher, get a longer lifetime and a good microstructure, etc. That's why when you choose manufacturing technologies, first you think whether we can forge it or form it. You choose this process. If you can't form it, if the it's too complicated, you use casting or 3D printing or something, other technologies. Or sometimes you say you can't get the right shape. for example, accuracy, you choose the machining to do it, or you do the combinations. We form the part, we do the last machining to get accuracy. And that's why the forming is a very important process, because the material becomes stronger and tougher. For applications of metal forming, if most people probably drive a car, you can see car body and chassis structures, 80% of components are manufactured through various kind of forming processes. Most of them are stamping, probably 50% of them stamping, some of the extrusion and some of them forging processes. You can say 80% of car body and chassis structure made using the technology is a huge use. Okay, and for aero engines and aircraft, for example, there are still a lot of majority of components are manufactured using forming processes. That's why I said the market is huge. And I encourage people to consider how to do more research in the subject areas, even if the forming process was developed 1,400 years ago or over 1,000 years ago, and it's very, very traditional technology. But nowadays, and there are global requirements for the new challenges for metal forming technologies and other technologies as well. One of the things we discuss is global warming. And people believe that global warming is due to the CO2 or the carbon and this kind of things get into the air and the pollutions, etc., and then cause the global warming. But I simply believe it because it's not my subject area. I think what we try to do, we try to reduce the CO2 emissions. And globally, people believe this, and I just simply believe this. And therefore, for passenger cars, for example, we try to reduce the CO2 emissions. Over the years, we try to reduce, goes down and down. In China, for example, this is the aiming to get something like this. In European countries and Japan, they are leading in the activity exercise, try to reduce CO2 emissions. But even though the global warming becomes heavier, and that's in 2002, before last year in the summer, in the UK, they announced this and give a warning. The temperature may increase to 40 degrees C for that day. Between London and Cambridge, there is a point, and the temperature reached to 37.5 degrees C for an hour. Very, very hot, and in the UK. And people in the UK, not like in Hong Kong, you have got a very luxury life. You have an air conditioner in your office, in hotels, your bedrooms, etc. In the UK, there is no air conditioners. And therefore, it's very difficult. But people in the UK are very innovative as well. This gentleman said in their rear garden, this is a rubbish bin. They put cold water in and with a glass of cold beer. In this way, they can try to protect themselves, reduce the heat from the body, because we have no air conditioner. We have no luxury life, but we have to protect ourselves. This is the way in the UK. But this is, I copied this from a newspaper, and in the newspaper, and I found it's very good. They are very innovative. And find a way to protect themselves. Okay, but here in Hong Kong, you don't need it. It's not necessary to copy these kind of ideas. Okay, and what we consider for transportation vehicles, the weight, if the weight increases, the total energy consumption increases. Like people, you try to reduce the weight and so on, and control the body weight, because if you are bigger and with big belly, for example, you use more energy for traveling. And this is a way we try to, this is the idea, we try to reduce the weight. We did a lot of data analysis for different kind of vehicles. We find that it's more or less linear ways to increase energy use if the heat if the weight increases. And we analyzed how to use the energy. If you for one person, if you travel for 1 kilometers, how much energy you use? If you do walking, you use 0.3 megajoules for 1 kilometers. If you use bicycles, this is the previous prime minister in the UK, and he likes bicycles. I used to use this bicycle. We call it Boris bike, and because he promoted this very much. And you use less energy, 0.1. If you use buses, cars, and aircraft, and trains, you use different kind of energies for travel for 1 kilometers. If you like to read the details for these, we have got more detailed analysis published in a paper in International Journal of Lightweight Materials and Manufacture. We analyzed this and tried to find strategies how to reduce the weight. But for passenger cars, for example, we try to reduce the weight, but the weight increases over the years. For example, for BMW 3 Series, and it was launched in 1975, and the weight is 1 ton, 1,000 kilograms. But now it's about increased by 50% the weight, because people like to have a big car, higher and wider and comfortable, and that's the life requirements. You put previously in 1970s, probably only 1 speaker there. Now is have 5 speakers with this kind of GPS, various kind of facilities. Then the weight increases, and also safety requirements. You have impact protections, various requirements. Then the weight becomes higher. If you analyze for the cars for many models, and with the different kind of models, this is the start launcher car. After 40 years for the model being launched, you found that the weight in average be increased by 50% over the last 30 or 40 years. We try to reduce the weight, but the weight increases. It's a contradiction. But how to do this? We need to try to make some efforts to reduce the weight. The purpose of reduce weight to save energy for driving it, and then reduce CO2 emissions. That's what we're aiming for. But to reduce the weight, first thing is the design obviously is very important. Apart from that, is the material selections. Now the materials, we use high strength steels, and the material becomes thinner and so on, then reduce the weight. Now we develop this for ultra high strength steel, and that can reduce the weight significantly. We said 20%. And then we can use composite and aluminum, magnesium alloys, and a composite. People have done research for many years for stamping for car body and chassis structures. Professor May have done this many years ago and continues as well. This more advanced research in the subject area. But until now, still only be able to use it for expensive cars like Formula One and with expensive cars. There are various kind of reasons I'm not going to discuss here. And what we recognize, probably aluminum, light alloys, aluminum, magnesium, titanium, and those are some materials can have potentials. If we look at aluminum, but now due to the manufacturing technologies, still be used for high rank cars. That's the expensive cars. And even if the fuel saving is higher and the CO2 emission reduction is expected, but due to the manufacturing technologies, we still unable to use for popular cars. That over the last few years or 20 years, we have made some effort in this area. Now I can report to you something. And for aluminum alloy or magnesium alloys, for example, the most important difficulties is the formability is low, is too brittle. You can't form complex shaped components. If you bash it and break, you can't form the part. That's the problem. But what we try to do, we try to develop a new technology to enable complex shaped components can be formed very cheaply. We generate technology called HFQ technology. Now we use trademark. And 15 years ago, I proposed the 3 words and generated a patent, protected in many countries, including China, Russia, Korea, Brazil, Mexico, Malaysia, etc., many Australia, many places, and plus European America and so on. And because most of people probably not in the subject area, I just give you a brief thinking about this, and I don't want to talk about detailed science, and just mention about technology, because for aluminum alloys, you need to do solution heat treatment. Once you do the solution heat treatment, you need to do quench to enable the alloys to be uniformly mixed with the aluminum matrix. That's the science. But what we do is during this, after solution heat treatment, we try to do the forming, because at that time, the material is very, very ductile. You can form very complex shaped components. Once you form it, once you form the component, you hold within the cold die. The die is water-cooled. Okay, you hold within the cold die to enable equivalent like a water quench. If you do heat treatment, you heat the material, drop into the water. Now I do not drop into the water. I put in the cold die, then hold within the die for a couple of seconds, then let the material quickly drop down the temperature, then get we call it a supersaturated solid solution of the material, and then form the part. And after that, we do aging, whatever heat treatment condition. Therefore, the heat treatment process has not been changed for the material, still optimized. Only difference is we find the window at that time, the material is very ductile. We can form the component. In the meantime, we compared with the traditional cold stamping process. We found spring back almost eliminated and no much spring back. This is good for the die design as well for stamping. Okay, I stop here for the principles. I don't want to talk too much about the science and the technologies, modeling, and so on. But what we try to do, once we develop this, and we try to commercialize this. For commercialize this, we need production lines with various kind of facilities. Then what I do is I organize 2 European projects, and one project we call the low-cost lightweight manufacturing technologies. That's come from 8 countries, 16 partners, and I was the coordinate to do this. And at that time, we formed these kind of production systems. And then before this project completed, I found other problems and I organized a second one. But similar to this one, initially I said localized 2, but the officer said it's not very good. I changed the name slightly, called low-cost material processing technologies. They're called LocoMatech. That's from 9 countries and 19 partners. Over the Europe, we try to reduce the cost by 20%, further 20%. That's what we're aiming to do. And but those 2 projects are very successful. We achieved the target, what we have done. I'll give you examples. Previously, probably you drive the car, the outdoor panels is very smooth, but we call it door inner panels are very complicated. The shape like this, very complicated. Previously, use deep drawing steel, you can manufacture in 1 piece of the panel. But when you change it to aluminum, it's difficult. Aluminum 5754, this is a very, very ductile, the most ductile aluminum alloy, almost most ductile. And then you still be unable to form the parts. Therefore, they split the part into 5 pieces that form individually, then use laser welding to weld the part together to form one part. But the cost is very high. Because of welding, various processes, you need 5 sets of toolings as well. But once you use HFQ, our technology, you can form back to one piece again. The cost from over 70 pounds back to about 40 pounds. The weight reduction can be a bit more if you use high strength material. You can achieve better results as well. Okay, this is what we have done. The tool donated by Lotus Automotive, and the parts that's been formed. The first time in the world to enable this part to be formed using high strength aluminum alloys. Previously, it's not be able to do this until now. People, apart from this technology, and having to find other ways to form this kind of part in one piece. And but you guys are much younger and more clever. Hopefully, you can find a better way to manufacture this component. And we did within the project, we did a lot of examples. This is a Fiat components that use aerospace alloys, 7075, and which is more brittle and difficult to form. They said it's not possible to form, but when they use our technology, they form this very easily. And this part is for aircraft 380, aircraft wing stiffeners, top wing and bottom wing to combine together. Currently, they're machined from solid block. The cost is huge, but now can be formed. This is a Fiat CIF, that's a Fiat B-pillar, the components between the 2 front and back doors that use high-strength aluminum alloys to form these. This is the group of people we did the job at that time. And what I would like to say is when we develop a new technology, we need to be patient, which takes time to do this. And for example, the work started for this particular technology. We started in 2003, that's 20 years ago, when I was at Birmingham University. When I moved to Imperial College at 2008, we continued to work on this, and we tried different kind of components. We established experimental science and so on, and also modeling techniques. Then in 2013, we established a spin-off company. After 10 years of the research, we established a spin-off company called Impression Technologies. And then afterwards, we collaborate with many places that manufacture components in 2016. And 2 vehicles, Lotus cars and Aston Martin, use the technology for their cars and have got starts the big impact for applications. Nowadays, the company is in Coventry in the UK. You're welcome to visit them, and they can see the applications of technologies now used for many places, and aerospace, automotive, and many other sectors as well. And this is our Coventry plant called Impression Technologies, and this is the outside of the company. Another technology I try to reduce is curved extruding technologies. And again, I'm not going to discuss the details of these, detailed science, but if anybody would like to know the details, you can look at the patent or the technologies. In engineering applications, many parts are curved like this. Okay, curved bumpers and front and back bumpers, and in trains, there are a lot of components are curved. That's the extruded profile and curved. But what we are doing now is we do the extrusion, we get a straight component, we try to use various kind of banding, stretch banding, roll banding, the Over 100 patents has been developed over the world, try to bend the different shape of the components, which is very difficult to bend. Sometimes it's not possible to bend. For example, you can get various kind of defects, features, and for bending. And could be very, very difficult. For many cases, we worked with the companies, it's not possible to do the bending for some part. And as I mentioned, people always think it's straight how to do the bending of the component to form the part. But what we think is whether we can extrude the components bend automatically. Then we develop a process with extruding the material with 2 RIAMs with a speed V1, V2, 2 speed. If you give the same speed to extrude, the materials come out here is straight. If the speed is higher on top, it's bent in this way. If the speed is higher at bottom, it bend in another way. You can control this very easily. Just change the speed, you can bend. Can get a snake shape. And you can do this very easily. We just changed the concept, previous concept. Once we develop this, people think it's that easy to do this kind of curved component. For example, this is the Morgan car give us chassis structures for the Morgan cars. There are many components here. For example, if you look at this in details, there are many pieces that weld together because they can't bend. They weld together. And to form this kind of a components is a bend component. But to use our technology, it's easier. You can get one piece. You don't need welding, don't need bending, and it's come out, it's bend automatically. It's very simple. That's why I said for conventional technologies, there are lots of rooms for innovation. But in the meantime, we found once the material come out, for example, if you extrude in this direction, it turns in another direction, shear strain create. And that's break the grain size, and then you can get very fine grain size. The grain size we find being reduced about 200 times because of the shear. You manufacture components, get very fine grain size, which is much stronger and tougher. That give you longer, we say longer service time, lifetime, fatigue life. Yeah, this is something extra advantages of these kind of technologies. We established the world first dedicated production systems for this kind of process. Okay, these are very traditional, but people says, give you 2 examples are very, very traditional. Extrusion and stamping being developed so many years. But I give you a little bit more advanced, but still metal forming. We forming micro components. If you use, we say electronics and like mobile phones, and you can see a lot of pins, micro pins. But for these micro pins, how to manufacture these in larger scale? And then we created a project, a European project, we call the mass production for micro component. That's the come from people, 38 partners, come from 11 countries. We organize this kind of huge project. Now, still the largest, one of the largest projects in the subject area in the world. And we try to establish a system how to manufacture micro components in larger volumes. And when we do this, we found the size effects becomes important. If you know metals, they have got lattice structures, slip systems in mechanics, slip systems, and that's grain size and orientation, grains orientations and grain boundaries plays very important roles for the quality of components. Therefore, we try to do the simulations, the analysis on this, but it's difficult for material how to create the green structures so that crystal plasticity finite element can be carried out to do the simulations. Then we spend almost 10 years to create a system called V-green, virtual green structures we can generate. And for doing this, we solved one specific problems. We use the probability theories. In the probability theory, there is a parameter we call C, and to control the probabilities. But for engineers, materials and mechanical engineers that do not know how to choose the C value. But what our idea is, we consider for a material, we know the average grain size, we know the maximum grain size, we know the minimum grain size. If we say if we say 90% or 80% of the grains within these boundaries, maximum grain size boundaries, then give these parameters, then that can determine, these are physical parameters that can determine the mathematical parameter C automatically. We spent 10 years to prove this one-to-one correspondence. If we give these values, only one C value you can determine. And that's we failed and try again, failed, tried again, and many PhDs, postdoctoral eyes worked on this, but eventually we did it and proved this mathematically. Then we can create the system called V-green, and we can generate green structures very, very easily, and also green boundaries as well for these. We call adhesive lines, green boundaries very easily. If we generate this, and also can assign the green orientations according to the probability theories. Green orientations, then we can stretch these, and the slip systems can generate, can be determined automatically. And then if we stretch the material for this, if we use traditional FE analysis, it will be shrink uniformly along the length. But if you use crystal plasticity-based FE analysis, you can find according to green orientations, and it's randomly changes. And this is according to the green orientations. These kind of features can be simulated, and if you would like to know the details, you can see the papers here. And we try to use this to model this kind of behavior of materials. So we extrude the micropins. This micropins is about 1 millimeter in diameter, and the grain size is about 211 microns. This grain size in average is about 32 microns for this. And this experimental work carried out by people in America, and we did the simulations. So we found the random bending for this kind of a larger grain size. For small grain size, we found it's very straight, because you can use a continuum model, a traditional macromechanics model to do this. The material selections is very important, and you can use these kind of facilities to select right materials for right components. And we did micropillars analysis as well. And another is the microforming of microtubes. That's is about one millimeter in diameter, and the thickness of these walls is about 40 microns. And we did an analysis, and papers published as well for this analysis. We found the failure mode for the materials and how to select the materials to enable the right quality of components to be manufactured. Okay, this is the microform forming very, very tiny component. And then another example, a fourth example I try to give is form a huge component for aircraft. And probably probably all of them use the aircraft frequently for traveling and for for upper and bottom wing panels, that one piece and about over 30 meters long is very big. And you need to make the component is light, high strength, and also bigger, good mechanical properties with a known lifetime as well. That's what that's the challenge for this kind of work. And show you something, and hopefully it works.
A passerby shot amateur video showing the wind fall off C-130 tanker plane just before it plunges to the ground. All 3 people on board were killed.
Yeah, this is a tragedy because the wind falls off, and then people on board all died. And this is something exciting. If you look at this carefully, if you look at the wing of the aircraft, one wing off, okay, this one is very exciting, but landed safely because it's this guy is very good skills and that can land very safely. But for our engineers, we can't trust them. We say our aircraft is not good, but our pilot are excellent. Can you buy would you like to buy the ticket for this aircraft? You can't sell it. You have to trust the aircraft, not the pilot, and not only the pilot. Okay, have to trust the aircraft. That's our job, how to do this. We need to manufacture this with a known lifetime. Here give you examples of the aircraft panels. This is kind of forming process we call creep edge forming. Is basically use a cover to cover the components, suck the air out, and then track the components onto the workpiece. And this is the furnace. We push this die under the panel into the furnace to do the heat treatment. We call the artificial aging. But during aging, creep occurs. Creep is the plastic deformation that forms the part. Very simple process. But sometimes it's difficult to control. What's the creep levels with the different kind of stresses, because it's bending, and on the surface high stress, and in the middle probably neutral surface there are no stress levels. What's the stress relaxation, and the creep occurs. And also at bottom part probably it's a compressive stress as well. And then we look at, because during aging the precipitate forms, the atoms moves, and those atom moves and the precipitations changes the creep behavior, plastic deformation behavior of material. We try to understand the mechanisms, and we try to create a constitutive equation to model this as well. At the end, we try to do is for the formed part, we know the yield strength and the mechanical properties. We need to do this kind of analysis. And we generate a system and a software for predict this. And this is a creep edge forming for a bit more complex shaped components that carry out in our laboratory. And for different alloys, if you tensile stress on the top surface and the bottom is compressive, you can get different kind of creep behaviors. For example, at same stress levels, the creep behaviors are a huge difference. And how to model this, how to predict this. And what's the precipitates, what's the effects to their lifetimes. That becomes a lot of science, but anyway, I'm not going to discuss in details on this. But there are huge research need to be carried out on this. In summary, for my presentation today. And I would like to say the traditional manufacturing technologies, such like metal forming, have a huge market. Okay, and a lot of applications, especially for transportation vehicles, and therefore need more innovations. But I'm not very sure how many people work on traditional manufacturing technologies here, maybe work on more advanced nano or whatever technologies. But I encourage people to think this kind of technologies is important and the market is huge. For example, we want to manufacture extra large, extra small components, how to do this. And and with the economical ways as well, with the complex shaped parts, with ultra high strength material, lightweight, and also high temperature alloys. And for these, how to manufacture these. Most importantly, we need to manufacture parts with a known microstructure distribution, with known mechanical properties and lifetimes. As I mentioned, I don't want aircraft fails in sky. We need to know this. What's the lifetime? Precisely to predict this. That's a lot of challenges. And most recently, everybody says artificial intelligence in metal forming is very, 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 very important. Currently, we have got many PhDs, postdoctoral researchers work on metal forming in artificial intelligence and use machine learning, deep learning, and so on. We published some papers. You can look at these if you are interested in. And what I would like to say, for the new current state, the new requirement for traditional manufacturing technologies, because of huge applications. That's why the new technology we developed, we can commercialize these using our spin-off companies, etc. This is what I would like to motivate young people to work in the traditional subject areas. Thank you very much.